Yeah, I think that's what's asking. I don't know if you can use this. I'll just use mine. Is it the final project?
Yeah, just create one saying project. I just want how I create this. But you should change the upload format to zip.
Okay.
Alright, so today we'll do, you see more of you than normal, which is a good sign, I guess. So it's a way for me to introduce you all to more of Interactable. But no, we'll do that for about an hour or so, and then we will, maybe 45 minutes, and then we'll do the read. Okay. So, right, so before we get there, so I just wanted to say that the makeup homework is due on Friday. Okay, and the project deadline is tomorrow. I just realized, so I somehow thought I created an assignment for this, but yeah, so Hong is doing it now. Hopefully he can, and you should be able to submit a zip file on Canvas. Yeah, so.
Any groups or something, or just one person in the group can?
Yeah, only one person. Yeah, like you did for the proposal, only only one submission for this. So otherwise, I'll just add a note saying that somebody else has been graded, like I did for this proposal. By the way, are there people whose proposals have not been graded? People who submitted very late or something like this? Because I graded early last week, but just curious to see if somebody submitted after that. No, good. All right.
So in all group, only one person graded.
Yeah, so in every group, only one person will be graded. The assumption is that you will share grades. Okay. So,
But how will it reflect in other person's canvas? When it will reflect already or?
oh no, it won't by default. But of course, I mean, we will do it later. Yeah. Okay. So you may not see it in your Canvas grades, right?
Yeah.
So yeah.
How many points is this assignment? Yeah, make it for 50.
Okay, and for the final exam, I yesterday night, it was late night, so probably you guys didn't notice, but I posted the practice finals and finals for the last couple of years. So do take a look, and note that we covered a little bit more stuff in the last couple of years. I used to go a little bit faster. So there may be a couple of things that you might see that are new to you. Okay, so if so, just ignore that. Right, so that's for the final of last year. Yeah, so any thoughts? Yeah.
Is the final just in this classroom?
Oh yes, so the final will be in the classroom, and I will announce a bit more detail. Yeah, so one thing to note is that you're allowed to bring anything you want, okay, but you're not allowed to use the internet. Okay, so if you want to use your laptops, it's fine, but download everything you want to use. Okay, so I mean, generally, you have to sign an honor code saying that you're not going to search for anything. Okay, and there'll be some PAs trying to enforce it, but of course it won't be perfect, so we'll rely on you guys to just stick to that. So, right, so it's everything offline and printed. And needless to say, communication is not enough. Okay, so, all right. So that's the final exam. Okay, so, and as I will say, the final exam is
It's not like water printed, so you can have it downloaded and looking at it on the laptop.
yeah. So you can logically incorrect. I agree. Okay, so yeah. So it's you can look at it on your laptop because earlier I just used to say printed, but then people would bring these really large sheets of paper. So it's better to just but yeah, don't use the internet. Any other questions? Okay, and it will be in this classroom. And confirm the time, but I believe it's 10:30 to 12:30. Is that correct? Yeah. Okay, so do confirm the time, and it's on Tuesday. Exactly what you Alright, so that's a little bit about final. So what I wanted to do today is do a little bit of recap about the NP completeness stuff that we've seen last week, and then we can move on to more broadly a review of the course. Okay, and today my goal for the review is to ask you guys about like certain homework questions that you probably found difficult, and maybe spend some time on that. So that's what the review part is. Okay, so before that, right? So let's recap what we did. So the last couple of weeks, we missed the Thursday classes most of the week. So I just want to do the review. So we start looking at complexity classes, right? We started generally asking what is the complexity of different problems, of solving different problems. we said that it's important to just look at decision problems. These are problems for which the answer is yes or no. And we said that most problems you can think of as decision problems. Even if you had an optimization problem to start with, you could phrase it as a decision variable. And we did how to do this. And we said that NP is the class of, it stands for non-deterministic polynomial time, and it's the class of all problems. These are decision problems again, for which a yes answer can be easily certified. Okay, and we said we had this picture. Now, canonical decision problem was you had a graph, and the question was, does this graph have an independent set of size k? So this was our canonical example for these things. And so the graph is known to the verifier. Okay. And now the question is, so this saying that this problem is in NP is like saying that there should exist a prover who can be like computationally unbounded, who produces a witness, okay, or a certificate. We call this witness and a certificate, such that this verifier accepts this witness only if G is a yes. And intuitively, we thought of this prover as just giving an independent set of size k. So if the prover just demonstrates an independent set of size k, verifier can easily verify that it is actually an independent set. Gets this set of vertices, checks that there are no edges, checks that the size at least k. So that is an efficient verification procedure. And all problems for which such a verification procedure exists, so those are said to be in NP. Okay, so that's the class of problems NP. Okay, so this is this is a notion you should all know. Okay, we said that a lot of problems are like this. We said that all puzzles are of this kind. Most problems we've seen are in NP. Alright, and last class we also saw this notion of reductions. Okay, and this we said is a very important notion. And basically, if you have two decision problems, which we call Q and Q prime, so a reduction is this mapping, which we denote by F. Okay? And this takes instances of one problem, instances of Q, to instances of Q prime, which is the other problem. Okay? And so what it should do is firstly the mapping should run in polynomial time. Okay, so it should take some instance I out here and map it with something. And so the yes instances must always get mapped to yes, and no instances must always get mapped to no. And typically this mapping function f will not know whether your instance was a yes instance or no instance. Okay, so it cannot solve the problem. So these are typically problems that we don't know how to solve efficiently. So, but we still are able to come up with reductions of this kind. Okay, so this is what we call a reduction. And so in this case, we said we'll use the notation Q reduces in polynomial time to Q prime. Okay, so this was notation. And this just stands for Q reduces to Q prime. And what are the uses of these things? We said that suppose Q reduces to Q prime. We said that if Q prime can be solved in polynomial time, then so can Q. And this is fairly obvious because suppose you can solve Q prime, right? Like there is an algorithm that can solve this problem, Q prime. Okay, that means given an instance, it can tell if it's a yes instance or no instance. Now, if I want to solve the problem Q, all I've got to do is first apply this mapping F. Okay, so I have some instance I of Q. I look at F of I. And I know that yes instance map to yes instance, no instance is map to no. So if I use the algorithm I have for Q prime to solve F of I, then I would be able to solve the problem Q on instance I. So this is what reductions are good for. So if this problem Q prime can be solved problem, then so can problem. And then we can turn this around its head, right? So you take the contrapositive, and if Q cannot be solved with polynomial time, then neither can Q prime. Okay, and this direction turns out to be very important in proving what I call hardness results. Okay. And these two things, we call them like proving easiness and proving hardness. So if you want to prove that a problem is easy, that is, it has some polynomial time algorithm, then you just have to reduce whatever problem you have to some known easy problem. Okay. So this is what I was saying, like if your Q is some known easy problem, and this we've seen examples, right? Like we've seen examples of reducing problems to flows and so on. Okay, like so that's one example. Yeah. So those are the kind of things I'm talking about. Reducing a problem to flows, or reducing a problem to linear programming, something. Okay, so these are all examples of proving that something is easy by reducing to something we know is easy. And this we do instinctively without even knowing. So that's, but formally that's what we do. And the other thing is proving hardness, which is reduce a problem that you believe to be hard to your given problem. This we haven't seen that many examples of, but I did state a couple last time. So you have certain problems that we believe are hard. Okay, I'll just recap satisfiability a bit. And you reduce that problem to your given problem. And this is one way to show that your problem is difficult. And you should be asking what are examples of hard problems, right? Because if you want to reduce something to your problem, then what is an example of a hard problem? We said that the canonical example is what is called satisfiability. And so for this problem, you're given a circuit. It has inputs something like x1, x2. So maybe x10. Okay, so you have inputs that are Boolean variables. This is a Boolean circuit. Okay, so if you don't know what these gates mean, it's nothing. So each gate is some AND or not. Okay, so this is like an AND, this is an OR, and so on. So it doesn't matter, right? So this is a Boolean circuit. Okay, it takes some Boolean inputs, true or false, and computes some value one. And so the question is that this is the satisfiability problem is basically this decision question. You ask, given this circuit, are there inputs, true, false values you can assign to these x1, x2 up to xn so that this y turns out to be true? Okay. So this is the basic satisfiability question. So do there exist values to these inputs so that the output is one? And yeah, so this is a very basic question, and we believe that there is no polynomial time algorithm for this problem. Like the only thing you can do is basically exhaustive search, just try all possible choices of this, and that will take 2 to the n time because you have to try all possible true-false assignments to each xi. And we don't know how to do much better than exhaustive search. Right? So this is the satisfiability problem. And actually, what is maybe I didn't stress this enough is that even though we don't know how to do better than exhaustive search, we don't know how to prove that this problem cannot be solved in polynomial time. In fact, we don't know how to prove that this problem cannot be solved in n log n time. Okay. So that's, you might say that this is the failure of complexity theorists, but that's the state of affairs. Okay? Like we don't know how to show that this problem cannot be solved in n log n time, where n is the size of this circuit. So, yeah, so we don't know how to prove this. And what this Cook-Level theorem, I'm not going to state it, basically says that any problem in NP, where NP is defined as this class of problems where there is an efficient verifier, can actually be reduced to SAT. Okay. And this is non-trivial theorem. We saw an idea of the proof of this. So this is the satisfiability problem. So any questions on this? Because it's important that you know what the satisfiability problem is. Because it's the quintessential example of a hard problem. And it's an example of a problem where we don't know how to do better than exhaustive search. Okay, so what is and this is a picture we saw last time, right? So if you reduce satisfiability to your problem, then you are making a statement that, in some sense, my problem is harder than SAT, and this is one way we justify our inability to come up with algorithms. Okay? Like you try coming up with an algorithm for a problem. This very often happens in research, right? Like you have a new problem you want to solve, and you realize that you can't come up with a good algorithm, and often the reason is that the problem is actually NP hard. Okay, so which is like saying SAT reduces to the problem you're trying to solve. And so this is the example we saw. I mean, this is the picture we saw. So, any thoughts, comments? Alright, so yeah, so the other thing that I wanted to quickly recap is last time we saw this notion of NP hard and NP complete. These are things also that I think every computer scientist should know, because almost in any area, right? Like if you take a machine learning class, you'll hear this phrase that, solving this learning problem is NP hard. Okay, so you should know exactly what this means. A problem is NP hard, so you say that Q is NP hard if SAT reduces to. That's like saying it's only harder than SAT. You know that SAT is a pretty hard problem, therefore being harder than SAT is some certificate of it being difficult. So this is how you should think of NP hard. And the problem is NP complete if there is a reduction to SAT and from SAT. Okay, so if there's a reduction in both ways. So Q is NP complete. If SAT reduces to Q and Q reduces. So often showing that your problem reduces to SAT is pretty easy. Okay, like we saw this for independent set, many problems. Most problems that you can verify the answer to, you can show that they reduce to SAT. Okay, it's the showing that SAT reduces to P, the first thing that's hard. So those are these notions of NP hard and NP complete that you should know. Okay, you know that you can't always solve them. Okay, so you have to make additional assumptions. You have to do other things. It's a useful thing to know because it, in some sense, is that can't hope to solve it in general. So let me be much more. Instead of saying don't waste your time, you can't hope to solve it. Any other uses of proving problems are hard? Yeah.
In the unlikely event that you do find an efficient solver and want to something NP hard to solve SAT.
Right. So okay. So that's sure. I mean, yeah. So you've solved SAT. So what? Right. Yeah. So okay, fine. So what he's saying is that proving that the problem is NP hard is useful because if you can solve it, then you have solved a whole bunch of other problems. Okay, so it has a lot of computational implications. Okay, like if you can solve it, you can solve a host of problems. Yeah.
So does this mean that the baseline is SAT in this case?
Yeah, so the definition of NP hard, just, yeah, so for the definition is basically that SAT reduces your problem. Right? So the baseline is in some sense SAT. Yeah, so it's only harder than SAT. Yeah, so there is this more general, and this is a field in itself, use of interactability, which is cryptography. Okay? Like sometimes it is nice to know that an adversity can't solve your problem. Okay? And this is often useful in security. Right? So this is one of the uses of hard problem. Right? So you want to somehow say that if some adversary can break my crypto system, then he can solve an NP hard problem, something like that. So that's a dream goal of cryptography. Okay? So we don't know how to do that, but you rely on other assumptions, like if an adversary can break my system, he can solve factoring and things like that. Okay, but generally, this is one reason you want to prove things are different. And it's a positive use case. And the final comment I want to make is the difficulty of proving P not equals NP. Okay, so as I said before, for circuit satisfiability, for this satisfiability problem, the best known algorithms are something like 2 to the let me just write, I don't know, some roughly n. Okay, so it's maybe it's a slight constant form than n. Roughly that. Okay, so it's almost like exhaustive search. Okay, but the known lower bounds are something like 10 n. So there's a huge gap between what we know and lower bounds. And the reason is that proving lower bounds is very difficult, as I was saying. Right? So these are some things that you should know about complexity of problems. Okay? So yeah, very high level, but these are things that you should know. Alright. So I thought I would, until around 11:30, I'm going to do a little bit of introduction to more of reductions. Okay, so and in particular, I wanted to give one example of a reduction, okay, because it's nice for you to see one example of a real reduction. Okay, so last time we saw a semi-example. We said that there is this problem. Okay, called 3-SAT. Okay. I should have put the definition of problem on this slide, but I accidentally. Okay, so 3-SAT is a special case of SAT. Okay, and so what is the problem? So last class we saw an outline of a reduction from SAT to 3-SAT. Reduction from SAT to 3-SAT means that 3-SAT is only harder than SAT. Okay, so that's why I have this notation. When you say that SAT reduces to 3-SAT, it's like saying 3-SAT is bigger in complexity than SAT. Okay, so that's one thing that this notation kind of is helpful. Okay, so right, so last time we said that even though 3-SAT is a special case of SAT, it is actually at least as hard. And I hand-waved the proof, but it's a very standard proof, so I'm not going to do that. And yeah, so what is the problem? Right, so let's see what the problem is. So it's you have some variables like you do in satisfiability. Right, so you have x1, x2, xn, but instead of having like an arbitrary circuit, now you have a very special formula that you want to make true. And your special is you have a bunch of clauses, and each clause we said involves 3 variables. That's why it's called 3-SAT. Okay, so it involves 3 variables. We call them zi1, zi2, zi3, and each z is either the variable itself or its negation. Okay, so it's either x1 or it's negative. Okay, so the z is sometimes called a literal, okay, but that's not useful for us right now. Okay, but you have clauses of this kind, and you have m such clauses. Each clause involves 3 variables, and it's an OR of 3 of these things, or the negative. Okay, so this is why it's called a 3-SAT problem. And the question that you want to answer, this is again a decision problem, is there an assignment to the xi such that all the clauses are true? Okay? So you want that each of these CIs has to evaluate true. Okay, so you want to find some xi so that each of these things values true. Okay, and we said that SAT reduces to 3-SAT, and if SAT reduces to any problem, that is, it's called NP-hard by definition. Okay, so that's why 3-SAT is NP. So this is something that we saw last time. And a couple of comments about 3-SAT is that it's a very basic NP-complete problem. I mean, and often people use this as the starting point for reductions. Okay, and you can see why, right? Like I said, that SAT reduces to 3-SAT, and if 3-SAT reduces to your problem of interest, there is some problem that you want to solve, then SAT also reduces to your problem. So, and that's like showing that Q is hard. Q is empty. So this is why 3-SAT is a very useful problem. Okay? People use that as the starting point. SAT is a circuit, it has some variables, a little bit more cumbersome. Okay, 3-SAT is clean, it just has 3 variables per clause, you just have one. So this is the starting point. This is another comment somebody made last time, is that 2-SAT is easy, right? So that's no big. All other problems are only harder than 3-SAT. And you can easily see why, because just add some empty variables. Okay, so this is true. Alright. So now let's so this is the example of a reduction I want to show you that. Okay? So we've been seeing the independent set problem for so long, and we saw 3-SAT. Okay? So I want to show that 3-SAT reduces to independent set. Okay? And actually, how many of you seen this reduction before? Interesting. Yeah. So okay. So maybe some of you have seen but don't remember. So that's fine. Okay. All right. So yeah. So what does it mean to do a reduction, right? So what you've got to do is you want to start with an instance of 3-SAT. So these are all instances of 3-SAT, and you have a few, some yes instances, some no instances, and you want to come up with an instance of independent set, right? And the blow up in the size of instances should only be a polynomial. Okay, so if this is instance of size n, this should be size poly. And yeah, so you want to come up with a mapping that takes an instance out here and maps it to an instance here. So how do we do such a thing? Right? So if you've never seen it, it's very tricky. So I'm going to show this reduction to you. But in general, one thing to remember is that reductions are very tricky. Okay, so it takes a little bit of insight and playing with the problem to come up with it. Okay, because ultimately what you're trying to do is cast one problem as a different problem. And other than some very simple cases where it's kind of obvious, this can be very tricky. So let me show an example. So what is an instance of 3-SAT look like? So you've got a bunch of variables, Okay, let's call them x1, x2, xn. And you have a bunch of clauses. Right? So you have C1, C2, up to Cn. So let me take an example for this. So for the purpose of this, so let's say I have x1 or x2 bar or x3, and this one is x2 or or something like that. So if I have a bunch of clauses like this, so what is the goal in 3SAT? I want to know if there is some exercises that each of these things evaluates to true. Right? So if I said like T F T F as x1, x2, x3, x4, then this one evaluates to true. Why? Yeah, so in this case x1 is true, so in fact both x1 and x2 bar are both true because x2 was false, therefore x2 bar is true. So both of them are true. And in fact all three are true in this case. But yeah, so now let's look at C2, right? So C2, all of them are false if you look at them, right? Like because x2 is false. X3 was true, therefore x3 bar is false. And x4 was false. Okay, so this is a bad assignment because C2 is not satisfied. And yeah, so our goal is to find some assignment for which I will use. So this is just to give you some intuition about the SAT. Alright, so the goal of SAT is to find an assignment, right? Now, how could we reduce this to an independent set problem? Because the goal of an independent set problem is to check if there is an independent set of size k. Right? And this looks very different from trying to find an assignment to some variables. Right? So that's the thing that you want to answer. Right? So it turns out that okay, so I'm going to show you the reduction because it will take a while with all such things. So, okay, so now let me consider the following graph. Okay? Because if I want to come up with an instance of independent set, I need to, an instance is basically a graph and some number k, right? And I want to know if the graph has an independent set of size k or not. So let me consider this graph. So where let's say for this graph, for this clause, I have three variables. This is like clause C1. For every clause, I have three variables like this. Because it is 3 sets, right? So for every clause, I have 3 variables. And this variable corresponds to x1. This variable corresponds to x2 bar. Sorry, I have 3 vertices. So this is a graph. Yeah. So, and here I have something corresponding to x2. Note that I have repetitions, right? Like if like x2 bar had shown up in some other clause, that clause thing will also have this x2. So I have 3 times m vertices. Okay. So this is the thing. And now where I'm going with this is that somehow, so what does it mean for a clause to be satisfied? Right? It means that one of these things has to evaluate to true. Right? So what I would like to come up with is an instance of independent set where I say clause 1 is true because xi is, let's say x1 is true. Okay? And clause C2 is true because some x4 is true. Right? So I could hope that maybe I want to pick one vertex from each of these clause groups. Okay, so every clause is a group of 3 variables. We have 3 vertices. So I could hope that somehow I have drawn edges so that from every clause, think of this as a cluster, say like a clause cluster or something like this. Yeah, from every clause cluster, I pick exactly one vertex in my independence. That's how I want to arrange. And one easy way to do it is to just put a key between these things. So if I put all these 3 edges, then and no independent set can pick more than one vertex in each cluster. Okay? So there's an easy way to ensure that you'll only pick one thing first. So now what you can do is that so it turns out. So if you don't follow this direction, by the way, it's fine. Okay, I just want to illustrate because I think it's very elegant and it's nice if you get somehow an idea of it. So, and reductions are always like this, okay, so they're always a bit nicer. Okay. So, with that caveat, okay, so let me proceed a little bit. Right, so you've got one, this is a new page, right? So you've got one cluster for every clause, each cluster has three vertices. And note that these things share some variables. This is some x1, this is some x2 bar, and this is some x. This was x2. And I said that I put a triangle so that these things never get equal. Alright, so I want one vertex out of these things. And I somehow would like that the vertices that you pick out actually let you read off the assignment. Like if you picked x1, then I would like to ensure that you don't pick x1 bar anywhere, okay? So that you can set x1 to true and make that, and that would be a valid assignment. Okay, so that's the goal. Okay? And an easy way to ensure this is to say that if I have an x1 here and I have an x1 bar out here, I can just put an edge between these two ones. Okay, and I can do this for every x1 bar. Right? So I have to do this between every x1 that shows up in one of the clusters and x1 bar that shows up in a different cluster. And this is nice because if you ended up picking this x1, you are not allowed to pick this x1 bar. Okay, and similarly you have an edge between this x3 and x3 bar, and so on. Okay, and maybe this x2 and x2 bar. So you've built this graph that has 3 times m vertices. Okay. So m was the number of clauses. M clauses, m variables. So this is in the SAT instance, 3 SAT instance I. Right? And your graph G has 3 m vertices, and the edges are basically the triangle edges. So edges that go within each clause, and edges that go across clauses between a variable and its negation. Okay, so these are in clause edges, and you have these across clause edges between xi and xi bar. So those are the kind of edges you have. And now I ask you, the goal is to say, does there exist an independent set of size k? Okay, sorry, of size m. Because I want to pick one vertex from each of these clause clusters. And that should be the vertex that will cause this clause to be satisfied. Okay? So that's the aim. And right. So what you can now show. So is this reduction kind of here? Okay. So we are saying that you will build a graph that your edges are of two kinds. One is this triangle within every clause, and the other is if I have a variable and its negation, I put an edge. And the rationale here is that if I made this clause be satisfied by taking this x1, okay, then I can't make any other clause be satisfied by picking x1 bar. Okay. That's exactly like saying that I set x1 to either true or false. I can't set it to both. Okay. So that's what this is capturing. And right, so what you can, and of course you can't have an independent set in which, if you have an independent set of size m, then exactly one has to be picked in, exactly one vertex has to be picked in each of these things because of that triangle. Because you have a triangle in each clause, you can't pick two things. So this is what can be shown. Okay, so what can be shown? I mean, actually, if you now go and think a little bit, you will be able to show this. Is that if we start with a yes instance of this set, we can find such an independent set. And it's a set of size m. This part is easy. Okay, you start with a valid assignment and you can show that this will be a valid independent set. And the other part which we have kind of shown is that if we start with a no instance, then you get a no instance. Okay. So this can also, and this requires the argument of the kind that I've been making. Like you prove this by contradiction by usually saying that, oh, suppose it's actually a yes instance, and then you will actually construct a satisfying. So that's the idea behind this reduction. Okay, and as you can see, reductions often take some effort, but it involves thinking like this. Okay, like how do I cast this problem as that problem? And often the problems will look very different, so you have to think of how do I convert this problem to this other problem? And that's often the challenging thing. So yeah, so I won't go too much more into this, but but I just want to show you one reduction because it's if I mean usually if I had a couple more lectures I would have done more examples of this and homework and stuff, but this time I didn't get to do this. And the other reason is also that usually you don't encounter complicated reductions. Most of you will not encounter complicated reductions. Like, only people working in certain areas do. Okay, so that's another reason I didn't focus too much on this. Like often the reductions you will encounter are ones where problems kind of are similar. They're not drastically different. Like in this case, the satisfiability and differentiate are fairly different problems. So it was tricky to come up with reduction. Alright, so this shows that independent set is also NP-hard. Okay, so the consequence of this is that independent set is also NP. Okay. And then that's because we reduced SAT to 3-SAT earlier, and now we have reduced this to independent set. And together it shows that SAT reduces to independent set, therefore independent set is empty. Okay. So that's what we've shown. And right, so the other thing that I just wanted to mention is the next thing you should ask yourself, given that there are NP-hard problems, is what about approximation? Right? Like for many problems that we've seen in this course, we came up with approximation algorithm, right? Like for this coverage problem and so on, said that you can find a solution that at least some constant factor is good as the optimum. Now you could ask, do such approximation algorithms that run in polynomial time exist for every problem? Right? Like maybe I can't solve an independent set, I can't hope to solve an independent set, but can I come up with an approximation point? Okay. Where the size of the set I find is always maybe half of the optimum, something like that. Okay. This is the next natural question to ask. And for a long time, people were able to find good examples of this, right? Like they could find, for many problems, they could find good approximation algorithms. Then people started asking, okay, but are there limits to approximation? Like, do you have problems in which you can say that that there is no, for instance, like let's look at our this. I forgot how we called it, but I think it was called this hiring problem. Maybe you guys don't remember, but we showed that there is a 0.63 factor approximation. Now, I mean, this was some maximization problem, and we showed that whatever we can cover is at least 0.63 times optimum. But you could ask, okay, so can I do better than this factor in polynomial? That's what I mean when I say are there limits to approximation. Right? And so it turns out that there is a very strong theorem called the PCP theorem. And what it shows is that there are problems for which even approximating is NP. Okay, and the reason this statement is non-trivial is because it's not a decision problem anymore, right? I mean, in some sense, approximation problems are inherently optimization problems. It's not like deciding between yes no. Ordinarily, all the reductions we saw are just reductions between yes-no problems to other yes-no problems. Okay? And there, this notion of NP hardness and reduction to 3-SAT were all very clear. The reduction from SAT is all clear. So the way this theorem proceeds is by saying, it's actually, I just wanted to give you this picture. Okay? So the idea is to take an instance of SAT and the idea is to, like before, reduce to the independent set is one example of a problem. You could have any other problem. But what you do is, these are now not yes or no things. Now these are graphs with independent set of size at least, let's say 2k. And these are graphs with max independent set having size less than k. So there's a gap between these. Okay, so I should not partition this into 2 pieces. Now there are 3 pieces. Okay, and so these are everything in between. Right? So you have graphs on, let's say, some poly n vertices, with independent side more than 2k, and these are graphs with less than k. So there's a gap between these two. And what the PCP theorem shows is that there is an efficient mapping function f, so that the yes guys go here and the no guys go here, and nobody goes to between. Okay, so this is called a gap-inducing reduction, because it's a reduction that induces a gap in the objective value. Okay, and you could ask how are such reductions possible? And this is one of the biggest achievements in complexity theory. So it took a long time and a lot of it. I think the first proof of this fact was about 150 pages. And there was a much simpler proof that came 15 years afterwards, just 30 pages. Okay, so that's kind of so that's why I won't show this thing. But this is a beautiful fact, right? Like that you can actually do this. Right? Like you can create such a gap in the So, alright, so what this shows is that, maybe I should just say why we care about this, right? Like if you can come up with such a reduction, now it should be clear to you that you cannot approximate the independent set problem to a factor, let's say 1.5. Because if you could do that, then you can tell whether you're in that case or in this case. Because if you promise that you are either here or here, then if you are there, you know that your maximum independent set was at least 2 times k. So your 1.5 approximation would have given you an independent set of strides which was strictly more than k, right? Because it was like 2 divided by 1.5, which is strictly more than 1. And so you know that you cannot be in this case. Okay, and this is how you can distinguish whether you were here or here. Because if you were here and you used the f, you got mapped to that. Yeah, so think about this a little bit. Right? So this implies, this kind of a reduction implies that you cannot even approximate. And what this guy showed when they proved PCP theorem was to show this for a bunch of problems. Alright, so that's all I wanted to say, okay, about hardness of computation hardness. Yeah.
So in this example, it's just A versus 2K. But that's like 2K doesn't seem bad. So 2K doesn't seem too bad.
Yeah, factor of 2 doesn't seem too bad.
So in general, is it like 2 or is it like much higher?
Right. So I removed those slides because we don't have time. But basically, what you can show is that it's a problem-dependent thing. Okay? And furthermore, there are what are called gap amplification. So for independent set, this is actually very easy. So in fact, the first time I did this course, I was very ambitious and I had this as a homework problem. People really did not like it, so I haven't taken this out. But basically, what you can show is that for independent set, if you start with a gap of 2, right? So then what you can show is that you can now go from a picture where you have less than k, more than equal to 2k. You blow up the graphs a little bit, so you can go to much bigger instances, where here it will be more than equal to 4k and here it will be less than k still. Okay, and you can keep doing this. Okay, and the graph size, if you start off the graph of size n here, be a graph of size n squared here, and so on. Okay, it will always be polynomial. Okay, and but you get increasing factors of hardness. Okay, so this turns out to be true for independent set. For other problems, there will be different limits. Okay, so there could be So for instance, for 3SAT, you can find a 7/8 approximation, but you can't get anything better, and stuff like that. Okay, so for different problems, you have different strategies. Okay, so there are whatever. So these are called gap-inducing reductions, and there are these things called gap-preserving, gap amplification, things like that. Okay, so there's all kinds of reductions that people have now come up with. Yeah.
Is this telling us what factor we could approximate?
No.
No.
So this reduction tells us, actually this reduction combined with this fact tells you that if you keep doing this, you cannot have any constant factor approximation prediction. Okay, that's what this does. Right? But for other problems, it does these kind of things may not tell us the right fact. Okay, so there are many problems for which there's a gap between the best algorithm and what we know to be hard. Alright, so good. So let's start with the review part. Okay, so we have about 20 minutes, ambitiously. So first I wanted to say, I want to start with like a little bit of my thoughts on the course, right? So this is probably the year which I've seen the most background, the most variance in the background of students, right? Like, so somehow, I don't know, it's just every batch is different, and this time I've seen quite a difference in the background, which is interesting. Which is probably why I covered less material than I ordinarily do, but hopefully it was done at the right level, which is why I also could not go into details of some places which I wanted. Okay. So and I've also, but on the positive side, I've noted that this year your homeworks are actually much more well reasoned than in the past. Okay. I mean, since most of you can make an argument, which is a great sign. Okay. So, I mean, in the sense that the high level is good, maybe the details can sometimes be tricky, but that's always a good sign. So what I've tried to do in the class is not to get too much into the details. For instance, I would have liked to do details of things like shortest paths, flows, and so on. And I didn't really do that, but this year I didn't go too much into detail because I don't know if they're too important. Okay, so one of the things to do when you're thinking about algorithms is to understand that details are hard and they are important, but they're not things that you probably need to remember going forward. Okay, like I know many serious researchers in theory who probably cannot tell you the details of a flow algorithm, okay, because they saw it 20 years ago and would not know. Right? So this is very normal. Okay. So what you should know, and this is hopefully what the homeworks illustrated, is that the details can be hard, and it takes a while to work out these details. But you should know that if you think right, you should be able to get there. Okay. So that's hopefully what you found. The homework on the project is also supposed to illustrate that sometimes pseudocode can be easy on paper, but implementing it takes some effort. Okay, so that's what you should know. And the main, I guess, take home from this course should be not just like a few subroutines that you gather here and there, although those are also important, but you should know like maybe how to think about algorithms, right? Like you should think of. In some sense, the questions we ask, right? Like, how well can you solve this problem? Some notions of space and time efficiency, and approximation is another thing that you don't often think about. Okay, but that's something very important in practice. And randomness is another thing that people don't often think about, and that's also very important. Right? Like, you might be able to solve a problem by use of randomness, which you cannot do in a normal way. And and this notion of efficiency and complexity are important everywhere. Okay, so that's something. Another thing is, which I forgot to write, is the importance of guarantees, right? So importance of reasoning. And the reason we try to focus so much on this course, in this course, is because you don't do it in other courses. This is the one place where you are like forced to do this. But hopefully you've realized that when you come up with an algorithm, it's not just coming up with the algorithm, but understanding when it does and doesn't work. So you may not be able to come up with formal proofs all the time. But you at least have to get a sense of when it works and when it doesn't. And this is becoming increasingly important, right? Because if you think about deep learning, right, nobody understands why it works. But at least we want to get a sense of what kind of things work, what kind of things don't work, right? So this, yeah, having an instinctive understanding, having some kind of an importance to this understanding is very important. Okay, so you should try to be as systematic as possible when you're trying to come up with algorithms. So yeah, so these are like general thoughts, and yeah, so here, yeah, I also wanted to like say a few things about these topics, but I won't really say much. Right, so some interesting things where this course could naturally go to, and there are other courses in the department that cover some of these things, are, yeah, so as I said, details of basic graph algorithm and stuff we didn't cover that much in this course. We covered them at a high level, but not like nitty-gritty detail. These, as I said, can be tricky. It's good for you to know them. Okay, but these you can find in most textbooks. Yeah, and as I was saying, these details are tricky and useful to know if you're actually solving this problem, but often the high level is what you should remember. Like, oh, there's some, yeah, if somebody says spanning tree, you should remember that, oh, there's this greedy algorithm that works. Okay? Like, you don't have to remember exactly what was done or something, or how it's proved and so on. But you should be able to come up with it given enough time. Right? So that's the ideal place where you want to be. Alright, so that's another thing about detail. Right, so about distributed algorithms, we didn't get to cover any of these in class, but this is something you see all over the place. Right, so I think there are a couple of courses in the department that are good about this. So yeah, talk to me if you're interested. And almost everything, all the algorithms we've seen are, all the data sits in memory and you're just analyzing. So some of you are doing some projects where that's not true, but on average, but yeah, most of you are not seeing algorithms, I guess, where you have different machines computing different things, you have to stitch them together and stuff like that. Okay, so there are many interesting challenges that show up here. So yeah, so this is an area by itself. The other kind of interesting model is making decisions on the fly. So this is again something people have to do all the time in practice, right? Like you have to, all of us have to make decisions on the fly, and there are these very nice models of computation called online models where you want to design algorithms that make decisions on the fly, but they compute with, but they try to compete with the best optimum in hindsight. So you try to say that, oh, my algorithm made these decisions and I incurred so much cost, but even if I had known the whole input beforehand, I could not have made a significantly better sequence of decisions. Okay. This may be impossible for certain problems, but surprisingly it turns out to be possible for certain. So yeah, so that's a nice model. Another thing, I have a very toy example in homework 6. There's about this notion of fault-tolerant computation. Right? Like because machines fail all the time and circuits fail all the time. So the question is, how do you do computation in fault-tolerant ways? How do you find where the problems were without like explicitly finding where the problems were, and how to recover and things like this. Okay, so there's an interesting analysis around these things. Okay, so this we did not get to do. And so this other thing is, how many of you have heard of quantum computing, quantum algorithms? You read the newspapers, you will have heard of them. So this is another buzz area, right? Like there's a lot of interest by a lot of people. The reason is that, we don't, here the caveat right away is that we don't know if quantum computers exist. And there's a significant number of researchers who believe that they cannot exist. Okay, Right, so with that caveat being said, so it's known that quantum computers can do interesting things. Okay? And the most famous example of this is that they can factor efficiently. So if you are given an n-digit number, there's a huge number, right? N is the number of digits. Then you can factor this number. Classically, we don't know how to factor a number in better than I don't know, something like 2 to the n to the 1/3 or something like that. Something exponential on a regular computer. But on a quantum computer, you can actually do this in time over time cube. So this was this famous algorithm by Shor. And what this will in particular mean is that all the crypto systems we use today would be broken if quantum computers were to exist. Okay? So like all of online banking and so on would be broken if quantum computers. Yeah.
What's the quantum computer?
Yeah. So that's I intentionally stayed away from it. Right. So basically, a quantum computer is one abstract way to model this is that you have these special bits called qubits, and the quantum computer, the regular computer just has some memory, right? Which has a memory is just a bunch of bits. Quantum computer also has memory, but these are like quantum bits. Okay, but how are they different, right? So these so I'm going to bundle these things called qubits. But the nice thing about qubits is that it's not like, so they don't have an, firstly, each qubit is a superposition of multiple states, right? Like an ordinary bit is either 0 or 1, and it's either 0 or 1, right? But a qubit can be a superposition of multiple bits. Okay, like it can be a superposition of 0 and a 1, for example. Okay. So it is, so it could be a superposition. And what is even more powerful is that if you have n qubits, they could all be what is called entangled. And in some sense, there is no way to describe one qubit without describing the others. See, that's what it means by entangled. Like if you mess with this bit, you could affect all the other bits. Okay? And so you've got to be very careful about how you manipulate these bits. Right? So that's the property of quantum bits, right? Like there's this phenomenon called entanglement. Okay. This is the reason people suspect quantum computers are not possible, because they don't expect like controlled entanglement like this to be possible. Okay. So it turns out that even describing the state, like to describe the state of an ordinary machine, you need just n bits, right? You just say this bit was 1, this bit was 0, this bit was 1, this bit was 0, so on. But to describe the state of a quantum computer, you need something like 2 to the n numbers. Okay, so you say that all these bits were 0 with some probability, all these bits were some other combination with some other probability, and so on. So this is the reason, so even describing a quantum computer takes exponential time. This is one of the reasons you hope that, maybe if you do something clever, you can solve exponential time problems. So that's so this is again the whole area in itself, and so we don't sometimes get this. So but there might be some courses, seminars on this at some point. Okay, so we'll come to it. Yeah.
So you don't have to actually, like, if you, actually it's awesome.
All right. So for that, these are things that you may want to look out for other courses if you're interested. And so I don't know if we have too much time, but just something about the exam. Some of you seem very stressed about it, but what I would like to say is that it's more of a sanity check that you've understood some of the main things that you wanted to convey in this course. And some things to keep in mind is that it will be much easier than the homework. Okay, if you spend a lot of time on the homeworks and you're used to doing that, it will be somewhat fairly easy compared to the homeworks. And you should always think simple. Don't assume that you will have. This is one I know some students in the past have said that homeworks are also difficult, therefore I expected this problem to be more complicated than it is. so don't fall into that trap. Think simple, and yeah, how to prepare for it. You don't have to read multiple textbooks and stuff. You try to identify what we did in class. So the next class I will actually go through each individual. I'll give you like a very short summary of each topic that we covered. Okay, and try to make sure you understand those kind of things. Okay, and you should know the details to the extent that you should be able to understand what you did in the homework. But not much more than that.